Good afternoon, everyone. We are grateful for this experience and opportunity we have to present, and we thank you as the listener. We're very excited to present our project that we have had from our process and controls dynamics class. Over the semester, we've had the opportunity to become well versed in how to create and implement controls in real world applications. And so for our project, we have focused on creating and generating a humidity controlled chamber. And so our primary objective for this project was to design and implement a humidity controller using an ESP32 microcontroller. And on the right in the image, you'll see what a typical chamber would look like. And ultimately, our goals are to minimize overshoot and achieve stable set point tracking. And also, when there are disturbances, to rapidly recover from those disturbances.
Here's a basic overview of what our physical system actually looks like, including a picture. It just includes common household items apart from our electronics, which includes a 3 gallon, basically a bin that's plastic with a lid, an ESP32 microcontroller, a DHT11 humidity sensor, which takes samples every 2 seconds, an ultrasonic atomizer that has an on off function, and an internal mixing fan. And we'll also have a video to show you really quick.
Okay, here's a brief video of our control system in action. So we have all our hardware just sitting outside plugged into our computer with our ESP32. And then inside our container, it's open right now, so it's never going to reach the set point, but we have our atomizer module, which is what puts mist into the air to control the humidity in the box. And on this end, it's not set up right now, but we have our DHT11, which senses the humidity and the temperature. And then a fan just down here is to circulate the air to ensure that we're getting a well-mixed environment to get accurate readings on our humidity. And it all feeds back to the ESP32 and our code on the computer, which controls the system and tells it when to turn on and off that atomizer so we can reach our humidity set point.
One of our first steps was doing some modeling and PI tuning in simulation. So we did a FOPDT model of that simulated step response where we got the gain of 46.77, our time constant of 31 seconds, as well as the dead time of about 30 seconds. We then did some PI tuning where we got the KC value of 0.055 and our tau of 31 seconds as well. Some highlights from this simulation is that the model predicted the system dynamics pretty accurately, and then our selected tuning minimized the overshoot and the IAE values. We then did the closed loop performance experiment where we got to see that the set point tracking took about 90 seconds for rise time from 50 to 80% relative humidity step. Our overshoot was less than 20% for all of our set point changes, and then our disturbance rejection recovered to within 3% within 1 minute after the disturbance started.
Here are our findings and limitations that we had from our project. We found some things that worked well and some things that were limiting. We found that our FOPDT model did, in fact, accurately predict our dynamics. The model-based design we had translated well to our hardware, and our results ended up having a close match between simulation and experiment because of our validated approach. As for limitations, our DHT11 did have low resolution and lag. Our binary atomizer caused small steady state oscillations. And potentially for improvement in the future, if we were to do this again, we would use better sensors and or proportional actuators.
And to wrap up with some applications of this project of what it would look like in the real world, a typical application would be a greenhouse climate control for optimal plant growth. If you had a scenario where you needed to maintain a set humidity despite disturbances like doors opening or people moving around, this would be a control setup that you could put into place to ensure that your environment is kept safe. And along with that, there's potential for biological or chemical storage if they need stable environments. We could implement this controller to ensure that our temperature and humidity sensor or readings are met. And finally, our key takeaways is that we did achieve tight set point tracking and rapid disturbance rejection, which was our ultimate goal, and we saw that this demonstrated practical control theory application to a real system, and that this could be used in the future for similar applications.